Welcome to this short little lesson on inclined planes and forces. So what we'll do is we'll start an object moving on a frictionless surface, and we'll just give it a little kick, and then we'll see, okay, what are the forces acting on this object as it slides across a frictionless table. So we've just paused it for the moment. It was moving at a constant speed to the right. This force that's going down, that's called the gravitational force. And the force going up is the force of the table pushing up on the block. This is called the normal force. And the normal force is 9.8, same as the weight. The weight pushes down, the normal force pushes up. The parallel component they're talking about here of force in this case is 0, because once the object is moving, according to the inertial law, it requires no more force to keep it moving at a constant rate. If you want to speed it up, you give it an applied force. If you want to slow it down, you apply some kind of friction or backward force. Okay, remember that the gravitational force is down and the normal force is up. Now let's reset and change the angle from 0 degrees to 30 degrees. So we'll switch this angle of inclination to 30, and we'll leave the weight the same. Notice now the normal force is 8.5, the parallel component of force is 4.9, and they even say that the necessary force required to push this plane or this object up the plane at a constant speed is 4.9, same as the parallel component. Now the reason they're the same is because if the parallel component is down and it's 4.9 newtons and then to keep the net force along the plane 0, you'd have to have a force applied of 4.9. So hence the parallel component and the necessary force or applied force are the same. Now because we have no friction, they are going to be the same. If we added a little bit of friction, then we would see that the applied force to keep this moving at a constant speed would have to be bigger. You can see that the gravitational force is still straight down. What we do in this situation is we resolve this using trigonometry, this pink gravitational force, into two components. One is the perpendicular force, the red arrow, that is perpendicular to the surface of the block. And then of course the blue line here is the parallel component of gravity. It's the one that pushes the block down the hill. This brown line that goes in the opposite direction to the perpendicular force is the normal force. Now remember that in the 0 degrees of inclination, the normal force and the gravitational force were identical. In this case, however, the normal force is only 8.5, whereas the weight of the object is still 9.8 newtons. The gravitational force, which of course is 9.8 newtons, is broken up into two components, the perpendicular force, and you can calculate that by using force of gravity times the cosine of the angle, in this case the cosine of 30, and the parallel component going down the hill can be calculated using gravity, the force of gravity, 9.8 newtons, times the sine of 30. And you'll notice that the sine of 30 is a half, and a half of 9.8 is 4.9. The normal force is bigger, but that's because there's more of a push into the block than there is down the block. As we increase the angle to, let's say, 45 degrees, then you'll notice that at 45 degrees, the two components, that is the parallel component and the normal force, are equal. That is, the force pushing down on the block is the perpendicular force, that's equal to the normal force. The parallel component of force is also equal to 6.9 newtons. The reason that they're equal is because the sine of 45 is the same as the cosine of 45. As we increase the angle even more to, let's say, 60 degrees, then we get, of course, a much greater force acting down the hill and less of a force into the hill. Now to notice that the parallel component is 8.5 newtons and the normal force is only 4.9. Again, because this time the cosine of 60 is a half, and therefore the normal force is a half of gravity, and the parallel component is much greater. Now if we add friction to the game, let's just make this 25 degrees, and if we add friction, so if we make the coefficient of friction, let's say something like 0.3, then what that's going to do is add more of a drag as we try to pull this block up the hill. So there's our applied force, and notice that our applied force has to overcome two forces in this case. It has to overcome both the parallel component of force, which is 4.1 newtons. It also has to overcome the force of friction, which they've calculated for us, is 2.7. So 4.1 plus 2.7 gives us a total of 6.8 newtons of necessary force in order to move that block up the hill with zero acceleration. All right, it's moving at a constant speed. It's not speeding up, it's not slowing down. Therefore, the applied force up is the same as the total force down, which is, of course, parallel force down and force of friction holding you back.